Mr. Collard. Welcome to the basics of the periodic table. In this tutorial, we will examine who was Dmitri Mendeleev, look at the contribution of Henry Moseley to the development of the periodic table, discuss the basic structure of the periodic table, classes of elements, the term allotrope, and discuss physical states of elements. Dmitri Mendeleev. There were many people working on the relationship between elements and attempting to even organize them into a table, but this is the man who's credited with producing the first periodic table. His periodic table arranged elements in order of increasing mass. Elements placed in the same group have similar properties. Mendeleev was the man who recognized this. Henry Moseley is credited with rearranging the periodic table based upon atomic number. This is the current arrangement for modern-day periodic tables. Henry Moseley developed the periodic law, which states the properties of elements are periodic functions of their atomic numbers. As atomic numbers increases, we can see regular trends in the properties of different elements. The term periodic means repeating or recurring, something that occurs at regular intervals. Let's look at the structure of the periodic table. The periodic table is arranged in vertical columns called groups and horizontal rows called periods. The vertical columns or groups, in your New York State reference table, you have the term group written right there. Group 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, up to group 18. You can see the term period right here. Period are the horizontal rows. Let's discuss periods. They are the horizontal rows numbered 1 through 7. We look at the whole row when we examine a period. We always examine them from the left to the right, never the reverse. It's important to note that elements within the same period have the same number of occupied principal energy levels. Occupied just means that electrons are in the shell. Occupied, if you think about it, does not necessarily mean totally filled. An electron can occupy a shell and not completely fill that shell. Elements in the same period have valence electrons in the same principal energy level. If we examine period 4, potassium through krypton, and we zoom in, as we do here, at these electron configurations, we can all see they have 1, 2, 3, 4 shells in every case, and the outermost shell is the valence shell. They all have electrons in that valence shell, which in every case in period 4 is n equals 4, or the fourth shell. The fourth principal energy level. The number of valence electrons is not the same, they're just in the same shell. Let's examine groups. Groups are vertical columns and they are given numbers 1 through 18. For groups 1, 2, and 13 through 18, elements within the same group have the same number of valence electrons. Exception, helium only has 2 valence electrons, but the rest of group 18 has 8 valence electrons. What is the maximum number of electrons in the first shell? 1 squared times 2 is 2. So helium in that first period can only have a maximum of 2 electrons. The rest of group 18 has 8 valence electrons. Members of a group have similar chemical properties. Lithium on through francium, they're going to react chemically in a similar way. If we look at group 2, they will react in a similar way chemically. Let's discuss classes of elements. Physical properties. Describe characteristics that do not change the identity of the element. Many physical properties are listed on your reference table S, including melting point, boiling point, and density. Let's discuss characteristics of metals. Metals are predominantly located to the left on the table. They're generally solids at room temperature. An exception is mercury is a liquid at room temperature. They have luster, malleable. They can be made into sheets. Think of a mallet. A mallet is a hammer. So if you hammer something, you can flatten it into a sheet. Metals are ductile. They can be made into wires. Metals are good conductors of heat and electricity. I'm sure you've encountered this in real life where you've touched a hot metal stove, a frying pan made out of iron. Here's some terms that are chemical properties. They are terms you're not familiar with. We're going to spend some time with them in later tutorials. Metals have low ionization energies and low electronegativity values. Chemical properties governing much of chemical reactivity. Metals are electron donors. They give up electrons. They will form, as a result, positive ions. Let's talk about transition metals. These are a special class of metals. They are found among groups 3 through 12. They're typically hard solids. and they typically have high melting point. Tungsten, symbol W, has the highest of the melting point of any of the elements. Mercury is a liquid at room temperature. A feature of transition metals is that when they are in water-based solution, we have a term for that, it's called water-based or aqueous solution. They make the solution colored, and they form very characteristic ions, and a lot of ceramic glazes are made out of transition metals in water-based solution to give very, very vivid colors. Transition metals can form differently charged ions. Copper is a transition metal. Copper can form either a +1 or a +2 ion. Sodium, not a transition metal, can only form a +1 ion. Let's talk about the characteristics of metalloids, also known as semimetals. They are located along the staircase, separating the metals from the nonmetals. We can see that the metals here are in red, the nonmetals are in blue, hydrogen, on the left of the staircase. This is what I refer to as the staircase. This black line right there. Take a moment to identify that on your periodic table. Did you do that? Do you see what I'm talking about? That bold-faced staircase. You need to memorize the 6 metalloids or semimetals: boron, silicon, germanium, arsenic, antimony, and tellurium. So right now I'd like you to stop the video, use a pencil, lightly shade those 6 elements. Let's focus on the nonmetals that don't include group 18 just yet. Group 18, we'll examine it in a minute. That's a special case of nonmetals. They're to the right on the periodic table, to the right of the staircase. They tend to be gases. They tend to be molecular solids. Now, there's a term we're going to use quite a bit as we go through the course. It's associated with a certain kind of bonding called covalent bonding. There's something called network solids, another type of chemical bonding. In the solid phase, they are brittle, meaning they shatter. This is the opposite of malleable. They lack luster. Another term for that is they're dull. They are poor conductors of heat and electricity. Chemical property here, high ionization energies, high electronegativity values. Again, more on those terms coming up in later tutorials. Here's a good definition of nonmetals and their chemical activity. Nonmetals act as electron acceptors. They want to take electrons from something, and as a result, gaining electrons, you know they form negative ions. Some examples: sulfur, phosphorus, bromine, which is a liquid at room temperature. Let's look at characteristics of noble gases. This is a special type of nonmetal. They are in group 18, the rightmost group on the periodic table. They don't have the properties quite like other nonmetals. They're generally non-reactive because they have a completely filled outer valence shell, associating the idea of chemical activity with valence electrons. Noble gases have a full outer shell. They don't need to gain electrons from another element. They are non-reactive as a result. With the exception of helium, they all have 8 valence electrons. Take a moment to look at your group 18 and look at the valence electrons as you work down group 18. They all have 8 valence electrons. Helium only has 1 shell in its atom, and we know in n equals 1, according to 2n squared idea from atomic structure, there can only be 2 electrons max in the first shell. So that first shell is filled with 2 electrons. Helium is non-reactive as a result, even though it doesn't have 8 valence electrons. They tend not to form compounds unless under extremely high pressure and extremely low temperature. In that situation, you can force krypton and xenon to bond under these environmental conditions. That is why all of the noble gases have 0 in that upper right corner of their element box in the periodic table. Except for krypton and xenon, there are some charges there. More on that when we get to the bonding unit. Let's talk about allotropes. When nonmetals exist in 2 or more forms in the same phase, so we can take the oxygen, the molecular form, which also, like bromine, has a subscript of 2, versus ozone gas, which has a subscript of 3. Molecular oxygen, or O2, versus ozone are all made of oxygen atoms. The bonding is different. We can look at the idea of an allotropes having different physical properties and also chemical properties. Oxygen gas, O2, has very different chemical and physical properties relative to ozone gas, O3. Let's talk about carbon allotropes. They can be graphite, which is what's found in a pencil. Pencils are not made out of lead. They are made out of graphite, and graphite is a pure carbon substance. So are diamonds. And so is something called a Buckminster fullerene, which is made out of 60 carbon atoms. These are allotropes of carbon because they are 3 structures with very, very different physical properties. Graphite, you're probably aware, is very, very soft. Diamonds are very, very hard. Buckminster fullerenes are used in a lot of organic chemistry and medical drug delivery applications. And I also want to bring up another one called graphene, which is an incredibly interesting substance made out of pure carbon, which has very, very different physical properties compared to graphite, diamonds, and Buckminster fullerenes. You might want to Google that sometime and watch some videos on it. It's incredibly interesting stuff. Let's finish up with states of elements. At standard temperature and pressure, we have an abbreviation for that. It's called STP, the information on your New York State reference table A. 101.3 kilopascals of pressure and a temperature of 273 Kelvin. Most elements are solid at room temperature. The exceptions are what we want to key in on. Mercury, which we know is a metal, and bromine, which we know is a nonmetal, they are liquids at room temperature. I would be very familiar with those 2 exceptions. Here are these subscript 2s again. Hydrogen, nitrogen, oxygen, fluorine, and chlorine. More on that as we get closer towards the bonding unit of where that subscript of 2 is coming from when we discuss the elemental forms of these elements. In terms of nonmetal gases, it's easy to remember all the elements in the noble gases or gases at STP conditions. Hydrogen, nitrogen, oxygen, those are probably familiar to you as gases. Chlorine is probably familiar to you as a gas. And this element, fluorine, that is also a gas. We can see droplets of mercury here. Here's bromine as a liquid, this part. And what happens here is this is called bromine vapor. Call it a vapor because bromine is leaving the liquid phase and going into the gaseous phase very, very quickly. But bromine is found as a liquid. This is my cursive L for liquid. Here we have fluorine gas, and here we have some chlorine gas. You might notice that characteristic green-yellow color chlorine gas. Chlorine gas is commonly referred to as mustard gas, which is a chemical weapon I'm sure you've heard something about. What did we learn in this tutorial? We examined Dmitri Mendeleev and his contribution to the initial formation of the periodic table. We looked at Henry Moseley and his contribution to the development of the periodic table, most notably organizing on the basis of atomic number. We looked at the basic structure of the periodic table, classes of elements, the term allotrope, and finally physical states of elements. Want to learn more about the periodic table? Check out Theodore Gray's website, periodictable.com. All images used in this presentation are affiliated with this site. Need more help? Please contact me. Have a great day.